Oh, you can't see it. Sorry. Thank you. Okay, good. So I was saying, right, so we're looking at the triangle inequality, right? And we were saying that the norm of u plus v is at most the norm of u plus norm of v. This is like stuff we already know. We proved this. The difficult part in this proof was mostly showing that when this inequality is saturated, it's where to use the previous results and argue about the real part and so on. Okay, so that was this part. So today we're going to look at, we'll essentially finish this section. So we're going to look at another result, which is called the parallelogram equality. Okay, so what it says is the following, right? So it says, so suppose you have a parallelogram. So let's build it. Okay, you can see the picture already. So you have a vector u, you have a vector v. Okay, and we write the vector u plus v. Right? Then obviously this vector is also v, this vector is also u. Is that okay? All right. So the sum of these, so the sum of squares of lengths of diagonals. So this and this, right? So the sum of squares of these diagonals. So u plus v. And u minus v. So the diagonals, right? The squares of these has to be equal to what? The sum of the squares of the lengths of the four sides. Okay. So the four sides would be u square plus v square plus another u square plus another v square. Correct? Is that okay? Is the statement fine? Okay. How do you prove it? Well, basically you just yeah, the proof is very simple. So you start with the definition. So what is the definition of norm? So norm of a vector is what? It is u. That's correct, right? Okay, so how do we write it? So we have u plus v, norm square would be u plus v, right? This you can expand similarly, plus u minus v. Yeah, sorry, thank you. Yeah. Okay, that's important. Otherwise, it would be a square root. And somebody had also asked, I don't know where the person is. Somebody had asked if we have square roots in regular fields. Okay, so there was a question, right? So when we are discussing all of this, assume that the field is either the real number or the complex numbers. Okay, so it's one of these whenever we are talking about this, because we're using things like square roots and so on, which are not defined in general for all fields. Okay, so that's sort of the underlying assumption. Thank you for pointing that out. Right, so this would be the expression, and then you would have u minus v, u minus v. So this we can expand, and the expansion would give you u square plus v square plus we would have cross terms uv plus vu. Correct? Is this step okay? So I'm just expanding this term over here. Yeah, it's just by definition. And then one can do the same thing for the second vector. So it would be u square plus v square. And what would be the other terms now? Minus v comma, right? So these are two terms, but they cancel, right? So you get the answer. Is that okay? Make sense? Okay. So that's the parallelogram. I messed up the spelling. Parallelogram equivalent. All right. So now today we're going to start with section 6b, and we're supposed to finish it today. Okay. So I don't think I don't know. We'll see how far we get. But we will try our best. Okay. But regardless, remember it's a new section. For people who may not have followed so far, please stop. Please ask as many questions as you need. Do not let me continue until it's okay. And I will try my best to write everything down so that I anyway organically go a little bit slower. Okay, so if I stop doing that, point it out, tell me that I'm just rushing, and then I'll be more mindful. Okay. So the first thing we want to do is come up with the definition of orthonormal. So we already defined orthogonal vectors, right? So orthogonal vectors, let me remind you. So v and u were said to be orthogonal if the inner product was u, right? So v and u are orthogonal if, is that okay? That was the definition. Now we're adding this extra word called normal. Okay. So what does that mean? So we say a list of vectors. So yeah, okay. So let me read this part, okay, and then I'll write it down. So a list of vectors. So let's call them E1 to EM. Okay, these vectors are called orthonormal if there are two things that are satisfied. One is that each vector, okay, has norm 1. So what does that mean? It means that EI has norm 1 for all I. Correct? So that's one condition. And the second condition is that all vectors are orthogonal to every other vector. Okay, so what does that mean? That so one can write this basically as follows. So EI, the inner product of EI with EJ has to be 0 for all I different from J, correct? Is that okay? Is the definition clear? Okay. We can write it a little bit more compactly. We can write it as, so you can combine these two. So can be combined as the following. So EI, EK is the same as delta IK, right? For all IK. Is this clear? Okay, why is it? What is the definition of delta IK? Okay, anyone else? Okay, so delta IK is what? So the definition is delta IK is 1 when I equals K is 0 otherwise. Right? So that's the definition. So this is why these two conditions can be combined. Any questions about this? Is it okay? So, okay, so let's quickly look at an examples of orthonormal lists. So the first one is the standard basis in Fn. Okay, so the standard basis in Fn is, for example, as follows. So you have 1, 0, 0, right? Then you have 0, 1, 0, like this. Correct? This is the standard basis. So what are the conditions we have to check for it to be orthonormal? We have to check one, that it is each vector is normalized, right? And second, that they're all orthogonal to each other. So normalization, so it's clear, right? So epsilon I, the norm of epsilon I is what? Each of these, so this is epsilon 1, this is epsilon 2, or whatever. Right. I'm following the notation from the previous book. Maybe I think that was. So what is the norm of epsilon I? Yeah, it's 1 because there's only one entry. And what about epsilon I in a product with epsilon j? So what would this be? Yeah, so this would be essentially delta H. Right? So we actually didn't even have to check this. This was enough. Correct? Is that fine? Making sense? Okay, good. Now here's another example. So it says the following forms an orthonormal list in F3. Okay, so the following forms an orthonormal list. So what is the list here? So okay, so what do we want to check? We want to check that the norm is 1, right? So okay, so this is the question that we're given, 1 by root 3, 1 by root 3. Okay, and minus 1 by root 2, 1 by root 2, and 0. Okay, so what would be the norm of this vector? What is the norm of this vector? Okay, why is that? How do you see it? Yeah, so how do you do it? So you do 1 by 3 sum. Okay, it's 1 by 3 plus 1 by 3 plus 1 by 3, right? 3 times. Because you're taking the inner product from both sides. Yeah, so you're doing this, right? So you're doing 1 by root 3. Okay, let me just write it up. So it's right? So we do row times column. Okay. That's how we define the norm, right? Essentially. Correct? Okay, when you take the norm, what do you get? You get this this 1 by 3, 1 plus 1 by 3, which is 1. Is that okay? Make sense? Okay, similarly so what about this one? 1 by root 2, 1 by root 2, 0. What is the norm of this vector? Yeah. Why is it 1? Because we do half plus half, right? Okay, good. So this is fine. Good. And now we have to check orthonormality. So how do you check orthonormality? Sorry, orthogonality. You've checked the normalization. Now we're going to check orthogonality. There's only 2 vectors, so you just have to make sure that they're orthogonal to each other, correct? So how do we do this? We take the inner product. So let's do that. 1 by root 2, 1 by root 2, 0. And then you have 1 by root 3, 1 by root 3, 1 by root 3. Okay. So what would be the answer? You'll get minus 1 by plus 1 by, okay, which is that okay? So that's sort of the idea of what orthonormal is. Okay, so the last one I'll leave you as an exercise. Okay? So this is for you to check. Okay. Now proposition 6.25 says, okay, any questions so far? Is the definition okay? Is it making sense? Is everything reasonable? Okay. So proposition 6.25 says the following. It says that the norm of an orthonormal linear combination is as follows. So if E1 to EM is an orthonormal list of vectors in V, then sum over I, AI, EI. So it's okay. Again, I started reading. I should write it down. Let me do that. Give me a second. Let me make some space. Okay. So right. So what is the statement? So proposition. You can read, right? Still, or is it too small? Can you read? Is it okay for people? Okay. So proposition 6.25 says. So if if E1 to EM is an orthonormal list, of vectors in V, right? So if you have some list of vectors that you know are already orthonormal, right? Then the claim is that if you take any linear combination written in terms of this basis, okay? So this is essentially some arbitrary vector, right? Where the coefficients are AI, correct? So if you take any such vector and you want its norm, you basically can read it off by looking at the coefficients, taking its absolute value, squaring it, and summing it. Is the statement okay? Okay, this sort of tells you that having an orthonormal basis makes it very easy to compute norms for vectors, for example. Okay, that is the statement. Okay, so for all A1 to AM in the field. All right. So why is that? So does anyone have an idea how you would prove something like this? Okay, so I'll give you a hint. You have to recall the fact that Pythagoras theorem. I may have spelled it wrong. Okay, so Pythagoras theorem says what? It says that for orthogonal vectors, essentially, for orthogonal vectors, U1 plus U2 plus UK, right? The norm is what? The norm is just the norm of these guys. And is that okay? You can text. If you need to talk, just text. It just disturbs me. That's the only thing. You know, it's I understand, like you guys are also trying to get your best done. It's okay. Is that fine? This is Pythagoras theorem, right? Okay, so who wants to tell me how to prove this statement about? So you have to use this fact one, and you have to use the fact that these vectors are orthonormal. Okay. Any ideas? Are you? Exactly. Yeah, exactly. So let's do that. So we have AI, EI, right? Sorry, we have the sum here, sum over I, and then we have the mod. Okay, so we can use the fact that they're orthogonal to write what? We can get the sum outside, correct? Get the sum outside, we'll have AI, EI. Is that fine? We're just using Pythagoras theorem. We're not doing anything fancy. Is that okay? Okay, and once you've done this, now what do we know? Exactly. So AI is a scalar, and then you have the norm of EI. And what is the norm of EI? Okay. And what was the statement? This was the statement. Reasonable? Yes? No? Any questions? J, S, is on the one answering L. Yeah. What is your initial actually? Tell me. What's the second letter? M. Okay. M. Yeah. Yeah, I'll leave it as an exercise, right? So if I have u plus v, this norm is the same as norm u plus norm v, right? Okay, and v is actually, I don't know, say w plus z, right? And they're also orthogonal, right? I can apply the same thing again, right? It's straightforward. There's nothing really difficult. But you're ready to point out that this is not exactly what we do. Thanks. Yep. All right. So let's continue. Here's an important corollary of this result. An orthonormal list is linearly independent. Oh, again, I started reading. Okay, so here's a corollary. So corollary. Oh, I have to say a little bit the following, okay, because this is a math class, so we should understand this. Normally, corollaries are for theorems. Okay, what I'm doing now is I'm writing corollaries after propositions potentially. That's a corollaries usually after theorems. So you state some theorem and it's a corollary of the theorem, like it's a derivative of the theorem, like a small consequence of the theorem. Okay. But what I'm doing now here, I'm abusing things a bit. I'm writing after propositions potentially as well. Okay, so don't do that in practice. When you start writing tables and stuff, don't do that. That's just a small little thing. Okay, so the corollary here says what? It says every orthonormal list of vectors is linearly independent. Okay, is the statement okay? So if you have an orthonormal list, right, we've not said anything about linear independence, right? We've just said that the inner products are different and the norm is one. So from this, we have to deduce that the vectors are indeed they're linearly independent. Is that okay? The statement okay? All right, so let's do that. Okay, so I'm going to make some more space for myself. Give me a second. All right. So, okay. So what does this thing say? It says, so what do we want to prove? We want to prove that an orthonormal list is going to be linearly independent. So how do we do this? So suppose E1 to EM is such a list, such a list. Such a list meaning it's an orthonormal list, right? So you're given this, and A1 to AM are elements in the field such that their linear combination is 0. So what are we doing here? We're doing the usual thing. When we want to show linear independence, we assume that suppose you could make them linearly independent using some coefficients, and then we show that all coefficients have to be 0. It's more or less the usual strategy. Yeah. Okay. So let's do this. Okay. So then we have that A1 square plus all the way to AM square have to be 0. Okay. Why is that? Right. So we know that here is you have a vector. So you have a vector which is supposed to be 0. Correct. So the norm of this vector will also be 0, right? And to compute the norm, what are we saying? We are saying that it's written as AI, EI, right? That's what the vector is. So the norm of this vector, exactly the same computation that we did earlier, right, would give you this, right? And then you can pull out AI. Okay, this is 1. Correct? So it's the same computation here, so you get this answer. Yeah, do it for now. We'll be straight. Thank you. So this statement is fine. Okay. And what can we say? So if you have a bunch of numbers, positive numbers, whose sum is 0, what does it mean about each of the numbers individually? Can they be non-zero? They cannot be non-zero, right? So they all have to be 0. So this implies for all I, AI has to be 0, correct? And what does that mean? That they're linearly independent. The only way for the thing to be 0, the only way that a linear combination of EIs is 0 is when all the A's are 0. That means E's are linearly independent, correct? Any questions about it? Is it fine? Okay, so that's basically what this thing is. All right. Let me make a little bit more space already so I don't get in trouble later. Okay, so now we're going to look at definition 6.27. So far we looked at the definition of an orthonormal list. Orthonormal list. Okay, so this didn't say anything about spanning the space, right? It was just a list of vectors. Now what we're going to do is we're going to upgrade this to being a basis. Okay, so for being a basis, like there are two properties that we need, right? The first property we need is linear independence. And what is the other property? It has to span, right? So there are two properties, linear independence and span. So linear independence, we already established that if you have an orthonormal list of vectors, they're going to be linearly independent. We just proved that, right? Okay, now what we're going to do is we're going to try to show that it also spans the space. Not try to show, we're going to define an orthonormal basis. Yeah, okay. I think that's the sentence. We'll define the orthonormal basis, and that would be doing both, right? It's already going to be linearly independent, and it would also span the space. These are two things. Okay. So that's the definition. Okay, so V is an orthonormal basis. Basis of V is an orthonormal list. Orthonormal list. Sorry, my handwriting is really bad because I'm trying to write quickly. Orthonormal basis. You can read the handwriting, right? Is it? You can still understand what I'm writing or not? Yeah. Okay. Sorry. Okay. Orthonormal basis of V is an orthonormal list of vectors in V that also span V, right? Is that okay? All right. Very good. Okay. So for instance, here's an example. So for example, what can you say about the standard basis in F2? Standard basis in, sorry, Fn. So what can be? Is it, so it's already an orthonormal list, we established this. Is it also a basis? Right, because it spans the entire space. We already know this, okay? So the standard basis, so this is an orthonormal basis. Okay, any questions? Please come in. So okay, so we can now proceed. We now look at corollary 6.28, which is basically a statement about orthonormal list. So it says an orthonormal list of the right length is an orthonormal basis. Okay, so you list the list has a certain number of elements. What we're going to argue is that if the number of elements matches the dimension of the space, then it's a basis. Okay. So we've done this before, right? Even with linearly independent vectors, we said that if you have enough linearly independent vectors, enough as in matching the dimension of the space, then it spans. It's essentially the same argument. So let me write the statement. So every orthonormal list of vectors in V with length meaning the number of elements in the list. Okay, number of elements in the list. This is what is meant by length. So of length dimension V is an orthonormal list. Is an orthonormal basis. I wrote what have I written? Orthonormal basis of. Is the statement clear? Okay. So let's see, how do you prove this? I already gave you the proof, right? So what are the properties that we are going to do? So first we're going to use the fact that an orthonormal list is linearly independent. Right? It forms a linearly independent set. Is that okay? I'm being a little bit sloppy, okay, with the writing. You have to write it properly in the exam. You have to say that an orthonormal list is a linearly independent set. So I must writing a few things short. Okay, so it's a linearly independent list. And then we can use our old fact, right? Like a set of vectors that are linearly independent, and are such that the size of the set, okay, is dimension V, implies the vectors span the space, span, right? Is that okay? This is like one of the things we proved in Hoffman and Kunz at some point. Yeah. Okay, you can go back and look at it. We already proved this. Okay, so the set of vectors in V that are linearly independent and are such that the set of the size of the set is dimension of V, then it would imply that those vectors span V, a combination of sets. Any questions about this part? Okay. So this is exactly what the proof is also saying. So from 6.26, it means that they're linearly independent. And this has size dim V, which means the text invokes this, but we already proved it in Hoffman. Okay. Any questions? Well, shall we continue? All right. Okay. So now there are a few examples to look at. So 6.29 says you're given a bunch of vectors. Okay, let me again make some space. Okay, so you're given these vectors, so half, half, half. Okay, half, half, minus half, minus half. Okay, and then minuses move around. Okay, so there's minus half, 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 half. Oh, did I mess up? And oh yeah, I missed one. This is the last one, and then you have half, minus half, minus half, half. Okay, so why have the signs been chosen like this? Basically to get orthonormality, right? Because we have to choose the sign so that you have, when you multiply them, right? So let's look at some of these. Okay, so if you want to show these two are orthogonal, when you take the inner product, what do you get? You get, okay, let's just count the signs. Okay, so you're going to get plus, plus, minus, minus, because the amplitudes are the same. Correct? Is that okay? Making sense? So this will give you 0. This is a quarter times. Yeah, and what about these? So it would be a quarter times what? You have a minus, you have a plus, and you have a minus. Is that right? Make sense? Yeah, and you can also do it for this part. So in the last part, you would have quarter. What would I get? Minus, minus, plus, plus. Okay? Is that okay? So these are all orthogonal. This is fine. Normalization. What is the normalization? It's 1. It's 4 times 1 quarter. It's for each of them, it's 4 times 1 quarter, which is 1. So they're orthonormal vectors. This is fine. And how many are there? There are 4. And what space are we in? So these are in F4, right? The 4-dimensional space. So 4-dimensional space, 4 vectors. We've already shown that they're orthonormal. So an orthonormal list of size dimension 4 would be a basis for that dimension 4 space. Yeah, you can check. I just did a few, but you can check. Yeah. The key point is that they always turn out to be 0. So it's been chosen. Okay. So here, this is just explaining that the norms are 1, right? This you can check. And then the inner product is showing you that, for some of them, like you already argued, you get plus, plus, minus, minus, and a quarter here, right? And this gives you 0. So this part is fine. Okay. And like I said, because we have an orthonormal list of size 4, in the 4-dimensional subspace F4, we can conclude that they form an orthonormal basis. Is that fine? It's just summarizing the argument that it is. Is that okay? Any questions? Is it clear? Is something missing? Tell me. Okay. Shall we continue? Is it okay? Okay. Right. So now there's some story part. So it says in general, if you're given a basis, say E1 to En of some vector space V, and you're given a vector V in the vector space capital. Okay. So we know then that for some scalars A1 to An, okay, so A1 to An in the field Okay, so there exists some scalars in phi is such that the vector v can be written as a linear combination of the bases, right? I'm not saying anything very complicated. Yes, this is just saying that a general vector can be written as a linear combination of the basis elements. This is fine. Now it says that computing these coefficients meaning AIs, okay, can be non-trivial, right? Can be difficult, let's say, for an arbitrary basis. If I give you some basis, okay, and you're given some vector and you're given some description of a vector, finding that vector in the new basis is not always straightforward, right? Because it's a linear interface, it can be hard. So it says that it's very helpful if the basis happens to be an orthonormal basis. Okay, then you can find these coefficients very easily. Is the point okay? What you're trying to do here? Okay, so let me say it again quickly. If you have a basis, if you have some vector and you want to express that vector relative to some basis, right, as linear combination, finding those coefficients can be difficult. Okay, but if you're guaranteed that this basis is an orthonormal basis, then there is a much simpler way of finding these coefficients, which is what we're going to look at. Is that okay? All right, so let's do that. Okay, so in this next result, so what we're going to show is, so the claim is that these AJs can be computed. Actually, it's not a definition. These can be computed, we'll show, as just the inner product of the vector that you had. So this is the vector, right, that you had, and this is the orthonormal basis element. Is that okay? Okay, so it's very, very clean. You don't have to do anything at all. Shall we continue? Is the statement okay? And is the statement okay? All right. So let's try to do this. Okay. So proposition 6.3 tells us the following. So this proposition 6.30 says the following. So suppose, like we said above, E1 to En is an orthonormal basis. Orthonormal basis of V, and this vector V belongs to capital V as well. Okay. Then V would be, this is the claim, right? So V would be, let me just write it more compactly, sum over I, V, EI, and the basis V. Is the statement clear? Okay, so if you have some basis and you have a vector V, it turns out that you can write this V in terms of this basis E as this linear combination, where each coefficient, this is what you were calling AI, right, earlier. So this AI can do it. Is the statement clear? Okay, so how would we prove something like this? Oh, sorry. And also the norm of this vector is just, this we already showed, so I don't think it's this part is hard. Right? We just use Pythagoras theorem again, right? For this part. Okay, so the norm of V square is going to be sum over I V here. Then using Pythagoras. Already. So we need to move this a bit to the top. Add some space for myself. Okay. So let's see how the proof goes. So what does the proof say? So the proof says that because E1 to En is a basis for V, okay, there exist scalars A1 to En such that V equals A1 AI EI sum over I. This is fine. This is just completely trivial. It's just from the definition of what a basis is. Okay. Now we know. Okay. So does anyone have any idea how to do it? How you would approach? So your objective is here to find. You have to find these AI coefficients. Okay. You have to find these AI coefficients. And you know that these EIs are orthonormal. So in particular, what that means is that EJ in a product with EI would be delta IJ. Okay. So what do you think what operation can we apply to this vector V so that we can extract this AI? Right. So we can take an inner product, right, with EJ, for example. Okay. So for example, let's try let's take an inner product with EJ. So if you do that, what you get is EJ V is the same as sum over I, AI, EJ, EI. Correct? Okay, and what do we know about this EJ, EI in a product? We know that this is going to be delta IJ from the definition of an orthonormal basis, right? So this we write as delta IJ. Is that okay? All right, so let's try to simplify this. So now what do we have? We have here sum over I, AI, delta IJ. Who wants to tell me what this will evaluate? Why? You don't answer. Somebody else. Why? Why? So the claim is that this is AJ. Why is it AJ? Right? You just use the definition, right? So what does this definition say? So you can split it into two parts. You can say I is not J in the summation, AI delta AJ. Plus this I can write it as follows, right? So I can write it as AJ delta JJ. Is that correct? I've just expanded the sum, right? So I've written the jth term separately there. So this object, this is one by definition. Okay. And here I and J are distinct, right? From the sum. So this would give you what? 0. So what is left? H. Is that okay? It's a very useful thing to remember. Okay. Whenever you see an expression like this, it is immediately going to only give you the jth element in whatever context you see. It's useful to sort of keep this calculation in mind. So you get AJ. Okay, so now what do we have effectively? We have that inner product of EJ with V gives us AJ. And that is what we claimed. Right? That is exactly what we said, that the this AI element can be written as inner product of VEI. So we said no, we said we can be written as AI. And now we found this AI to be inner product of VI. V with EI, sorry. Is the statement okay? Making sense? Okay. So okay, so let's see how it is formally written. So formally it says that take E1 to En to be a basis. I'm just repeating the argument now. Okay, so in case there are any gaps, you'll fill them. So E1 to En is a basis. Okay, so if that is the case, you can always write V as some linear combination in terms of coefficients. Yeah, right. And now we just proved, right, that AJ can be written as V in a product of V with EJ. Right, we just proved this. Okay. So what does that mean? That you can substitute for each. So A1 can be written as VE1, right? And AN can be written as VEN, right? And that is exactly the form we had in the third state. Okay, the statement was that each V can be written as. Is that okay? Any questions? Maybe I messed up the inner product. Yeah, okay. So I think we took the inner product on the left. You can also take it on the right. So wait, did I mess up? Oh no, I think I messed up because yeah, then you're right. That's a good point. Okay, so that's a very good point. Yeah, I will get an E bar in my answer. Why do I get an E bar? That is a good point. Okay, so I messed up a little bit when I was writing it because I was using the physics notation. Okay, this is math, so the vectors are a little bit different. I said in the beginning, no, there are two conventions. There's the physics convention, the math. I was using the physics convention, so be careful. Don't do that. Here, so remember that if you have a vector A alpha and you take the inner product with beta, this should be A bar beta alpha, right? So where this is scalar, and these are vectors. Okay, don't make this mistake when you're evaluating it. Okay, so this is the math convention, because here this part is where you get the complex conjugation. In physics, you get it on the left side. So be careful. But that's a very good point. Thank you. Okay, so I'll get A bar is equal to EIJ. Okay, so let's say this is A bar, and then it is consistent, correct? Because then you can take the complex conjugate and you will get H. Okay. Well, any other questions? Is that okay? All right, so let's continue. Okay, so proposition 6.25 says that the norm of an orthonormal vector, linear combination. Wait, what is this? I think it's asking for this. Yeah, this last part is sort of straightforward. If we already proved this, that if you have a vector v, right, you can, and if you are expressing it as sum over ai ei, right, then one can extract the ai as mod square and ei over here, which we give you one. This we already proved using Pythagoras theorem. Is that okay? S, you seem concerned. Is it okay? All right. L, is it making sense? Okay. Okay, very good. So okay, so let's continue then. Is the pace okay? Is it too slow? Is it too fast? Is it okay? Is it okay? All right. So okay, so now we've seen the usefulness of orthonormal basis. Okay. The question is, how does one find an orthonormal basis? Right, so suppose you're given some basis for some vector space. How do you construct an orthonormal basis out of it? Okay, that is sort of the question we want to understand. So for example, it says, does PM, so PM, remember, so the question is, does PM of R, so PM is basically just the set of polynomials, so it's a poly of degree at most M. Okay? So does PM of R, let's say you take the inner product, right? The inner product is with inner product integration minus 1 to 1 dx qx dx. Right, so this is like the notion of, because we are talking about inner product spaces, so we have to define inner products. Most of the times you're on finite dimensional spaces, and things are very, very easy. When we're talking about polynomials, we just define the inner product space, right? So the question is, does this space, right, this space, have an orthonormal basis? It's not clear. Right, a priori, it's not clear at all. Right, you have some strange inner product, you have some strange space. Can you actually construct a basis that satisfies that? It's not clear. Okay. So now what we're going to do is, so here we're going to basically answer these questions. Okay. So in the following section, we look at how to answer it. And one important algorithm in answering this question is called the Gram Schmidt procedure. Okay, so one important procedure to answer such questions is the Gram Schmidt procedure. Okay. So what is the Gram Schmidt procedure? Basically, it gives you a method. So okay, so what is this? It is basically a method. Method. Oh, actually, give me a second. Let me just make some space. First, yeah, sorry. Okay, I'm also sort of getting used to this new workflow, so it takes a little bit of time to optimize the moving around of things. Okay, so the Gram Schmidt procedure says what? It says it gives you a method for turning a linearly independent list, okay, linearly independent list of vectors, of course, into an orthonormal list. Oh, sorry, orthogonal list. Fine, orthonormal list, while preserving with the same span. Okay? So you're given a list of vectors which are linearly independent. You're going to apply this procedure, and this procedure would spit out a new set of vectors, okay, which are going to be orthogonal and have norm 1, both properties, so it will be orthonormal. And additionally, it would span the same space. Okay? So what does that mean? If your initial thing was a basis, the new thing will also be a basis. Okay? Making sense? Yeah? Okay. All right. So let's do that. Let's see how to do Gram Schmidt. Yeah, actually, before we do that, maybe we can take like 2 minutes and think about it. So suppose you have a bunch of vectors. So you have, suppose U1, U2, U3. Okay, you're guaranteed that they are linearly independent. Okay, so you're guaranteed. guaranteed linear independence. Okay. So can we try to construct? Let's think about it geometrically. Okay, I think that may be the best thing to do. Let's do the two-dimensional case because it's easier to draw. Because I'm just giving you some intuition before I give you the thing, because then it's actually very, very trivial. There's nothing very complicated happening. When you write it down, it looks a little bit big and scary. So if you understand the idea, it'll be very, very straightforward. So, okay, so suppose you have two vectors. So let's call this vector u1, okay? And this vector u2. Because there are two vectors. They are linearly independent, right? Because you cannot write one as a scalar combination of the scalar multiple of the other. They're just different directions. There's only two vectors. Okay, so it's clear that u1, u2 are linearly independent. Correct? This is fine. Okay. Now what we want to do is we want to construct new vectors, say v and w, right? Such that the inner product of v with w is 0. So I'm just using the geometric intuition, right? So if they're orthogonal, the inner product is going to be 0. Okay. But I want to build them starting from u1 and u2 in some systematic way. Okay. So so u1, this vector, sorry. So okay, so suppose we want to fix u1 to be the first vector. So suppose we define v to be u1. So we fix the first vector to be exactly this. Now we have to construct the second vector w. Okay. So the second vector w basically should not have okay. So let me say the following. So this u2 vector, u2 has some overlap, okay, with u1. What does overlap mean? When you take the inner product, it's not 0. So there is some overlap. Okay. So what we can do is we can write u2 as some coefficient a1 times u1, okay, plus some coefficient a2 times some other vector, let's call it w, where w is such that it has no overlap. So no overlap with u1, i.e. u1 and w are orthogonal. Okay. So you want to say, okay, there's one component which is exactly along u1, and the other component, so anything that's along u1, I'll absorb that weight in a1, and everything else I will absorb in a2. Okay, I can do this. Okay. So the basic idea is that you want to write u2 as basically u. So this coefficient, right, we can find as u1a, sorry, u1 u2, right? Just using the same idea as we did in the previous session, right? That you're basically picking out the coefficient along this times u1, okay? Plus whatever is left, okay, along w2. So whatever coefficient is left, 1 minus u1, u2, something like this, along a vector w2. Okay, but w2 is such that it has no. Okay, so this is such that has no. Okay. So this would be. So okay, so what we're going to do now is, so this w2 is basically going to be defined. You know u2, you know u1, you know the weights. Okay, so one can define. So one can just use this as a definition for w2. It says u1 times some coefficient. U2 minus this divided by the normalization position of this vector. If you don't really care about, I mean, you could absorb actually, let's just say it's W2. Let's not worry too much. Let's just say it's W2, which is not normalized. And then we can define, so W2 has no overlap with, so no overlap with U1. Okay. So it has no overlap with U1. And W2, then we can define W2 upon W2 divided by the normalization. We can call it so W is just the normalized version of this W2. Is the idea okay? So let me say the idea one more time. The idea is you start with these two vectors, U1, U2. Okay. And what you're going to do is you're going to systematically remove the component that is already along U1. Okay, so that we are going to write as U1, 1. And then we're going to introduce a new vector such that it has no overlap with U1. Okay. And then we will use that as the definition for the next vector. Okay, that is the high level idea. So you start with a bunch of vectors, you remove the component along the common vector. Okay, what is left would give you the other vector. Okay, and then this process you can generalize. Okay, that is the high level idea. Does it make sense intuitively? Okay, we will make it formal, of course. And this is just for 2 dimensions, but the idea is you're just removing the component along the vector that you start with. Whatever is left, you use that as the definition of the next vector. Okay, and then you proceed similarly. You can keep moving. Okay, so let's look at it more formally, what it says. So the Gram Schmidt procedure says the following. So suppose, so let me make some space here. Okay, so it says, suppose V1 to Vn, okay, are linearly independent in the vector space V, okay, and we define E1 to be the first vector, but which is normalized. Okay, this is what we also did in the example. Right, we just define the first vector with the normalized version. This first vector. Okay. Now for J in 2 to M, we're going to define EJ inductively. Okay. So what is the induction here? The induction is you define EJ prime to be the VJ vector. So at the jth step, you look at the VJ vector. So here's VJ, you take the VJ vector, and you remove all the components from the previous vectors. Okay. So you're removing VJ, the overlap with E1 vector, right? You remove the overlap with the E2 vector. So remember, E1, E2 you've already defined, right? That is what it means. Like you've defined E1 to EJ minus 1. You're using that to define EJ. Right? So you're removing all the overlaps from the previous vectors. So VJ is this, okay? And so you do this process and you remove all the components along all the previous vectors. Okay? And whatever is left would give you a vector which doesn't have any overlap with these because you removed all the overlap. Okay, and that's very easy to see. You take the inner product with any of the previous ones, it will disappear. Okay, we will check. Is the intuition okay? So you start with the first vector. That is, that's perfectly fine. You assume you've done it for the j minus 1th vectors. Okay, and for the ejth vector, you say it is whatever the vector was, removing all the components along E1, E2, E3, and so on. That is all that is being made. And then your EJ vector, by definition, would be EJ prime just normalized. Right? Because they have to be, what is it called? Unit vectors have to be normalized. Is this making sense? Any question about the definition? Definition I'm saying, the statement, the theorem statement. Yeah. So, okay. So what did we want to do? We wanted to construct an orthonormal list, right? We're trying to construct an orthonormal list. So here, EJ, it will turn out is orthogonal to all the previous ones because we already remove all these components. Okay. We will prove this in just a moment. Okay. It's very, very easy. So it is orthogonal, but it's not necessarily normalized. Okay. So this part is just normalizing. Any question? Looks like people are a little bit lost. If you didn't understand the intuition, that's fine. Just mathematically, symbolically, are you able to understand the statement? That part is important, and then we'll prove it formally. Is the statement clear? No, it is. Okay, so then people are getting bored. Then okay, I see. All right. So if that is the first part, and the second part is of course that the span matches. Right. So we're going to also show that span also. Okay, so if you do this definition, then E1 to EM is an orthonormal list, and span of E1 to EM is the same as the span of 1, which is what we were saying in the beginning, right? That if the span of the initial linearly independent set is the same as the span of the output of the algorithm, right, which is these vectors, if they match, then we can also talk about basics, right? So if initially you have the basis, then this procedure will also give you a basis. Right? Making sense? Okay. Very good. So now let's maybe move things slightly. So I guess now we can look at the formal proof of how it is done. It's very, very straightforward. Okay. So how are we going to prove? We are going to prove this by induction. Okay, so we prove by induction on J. Okay. Okay, so to start with, we have that if you consider the J equals 1 case, okay, it's clear that span of, so for J equals 1, right, what was the definition of E1? It's defined as V1. It was just the first one. Yeah, just the normalization, exactly. Okay, so V1 by normalization. Okay, this is fine. Yes. Oh. Yes, you're supposed to follow. Okay. E1 is the definition of E1, okay? So E1 was just defined to be the normalized version of E1, right? Okay. So that is E1. Now, it's clear, right, that the span of E1 is the same as span of E1, right? Because you just did a scalar multiplication and the vectors are non-zero. Okay. So J equals 1, everything seems to be okay. And of course, there's only one vector, so there's no orthonormality condition to check. Okay. So now what we're going to do is we're going to suppose that for one, for the index J, strictly between 1 and M, okay, we have already verified what have we verified? Two things. So one is that the span of V1 to Vj minus 1, okay, is the same as the span of, excuse me, is the same as the span of E1 to Ej minus 1. So suppose we've already done this. Yeah, the jth step, we already assumed that for the j minus 1, we have the span condition. And there's only one condition. Okay, so suppose we have verified this. Okay. Now it says note that Vj cannot be in the span of V1 to Vj minus 1. Right? Because V1 to Vn are linearly independent. Right? That is just by assumption. Okay? So Vj certainly cannot be in this span. Okay. So this is fine. Therefore, E prime j cannot be 0. Okay. So what was E prime j? E prime j is just the normalized version. So Ej was defined to be what? So let's look at the definition. It was Vj minus a bunch of different vectors. Right? So it was Vj minus Vj E1 minus all the way to Vj E j minus 1, Vj minus 1. Right, and this span and this span are the same. So this is the span on E1 to Ej minus 1. Okay. All right, so we're using all of these vectors, right? And we've added Vj in the mix. So it's basically just think of it as a linear combination of Vj's and Ei to Vj minus 1. Okay. This linear combination cannot be 0, right? Because you have this Vj present, and Vj is not in the span. So there's no way you can make the linear combination. Okay. All right. Okay. So this is fine. So therefore, the norm of EJ prime, or sorry, EJ cannot be 0. Right? Because remember, norm has the property that the norm is 0 if and only if the vector itself is 0. Okay? So why am I saying all of this? Is because when we are defining E prime, there's a division by the norm of EJ. So we don't want a division by 0. So we're being very careful here. That is all we're doing. Is that okay? Okay, so we are ensured no division by 0. Okay. Let me make a little bit more space so we can write the argument properly. Okay. So this step is fine. Now what we're going to say is we're going to say we're going to take K to be strictly less than J, because it is some index which is between 1 and J. Okay. Then EJ, EK, if you take the inner product of EJ, EK, okay. So remember, K is strictly less than J. So if you take this inner product, what you're going to get is the following. So you'll have Vj. So I'm just going to plug in the definition of EJ. Okay, so what is the definition of EJ? It is Vj, and then you subtract a bunch of coefficients, right? So you subtract Vj, E1 minus, you subtract EJ minus 1, all the way to EJ minus, right? That is the definition of the new object. And we're going to take the inner product with EK. Okay? And I'm dropping the normalization. Okay, so there is some normalization factor, which some normalization, which we're dropping from, because that's non-zero anyway, so it won't contribute. Okay. So now when we take the inner product, what do we get? So remember EK, right. So what do we know about K? So K is supposed to be, so it's going to pick out one of these elements, right? When you multiply, it will pick out the kth element, right? Because otherwise all the others are 0. It's all. For the previous cases, we already assumed that they're orthonormal, right? So the only component that would contribute is Vj EK. So obviously this guy is the same, right? Minus, from the second term, what do we have? Vj, right? Because there would be some EK, right? Which is 1. And all the other ones would disappear. Is this step clear? Okay, this is important. Because, so what we used here, because EK is 0 when L is not equal to K. Right? So we use that factor. Okay, so this is what you get divided by some normalization. But that's irrelevant, right? Because this gives you 0. Correct? Because Vj disappears. Okay, all right. So what have we established now? We have established that using the fact that E1 to EJ minus 1 are already orthonormal, we've shown that EJ is also orthogonal to all the previous ones. Right? And it is already normalized by construction. And we checked that we are not dividing by 0. So it can be normalized, so it's not a 0. Right? So then we are essentially done, right? By induction. So we've shown that all of these vectors are orthogonal. Yeah. All right. So here, so let's finish the argument more formally. Let's see what this guy says. So from the definition of okay. So we still have to show the span statement. Okay. So we showed that it's orthonormal. We haven't shown the span thing yet. Right? Okay. So let's see how we show the span thing. So okay. So it says from the definition of EJ. Okay. So the definition of EJ here, this one, right? So this definition right here. So we know what the definition of EJ is, right? So EJ was, which was equal to Vj minus this exact expression. So Vj E, let's say L E L, sum L going from 1 to J minus 1. Okay, that's the definition of EJ. Normalized. Okay, so there's some normalization. So from the definition of EJ, it is clear that Vj, this vector, is in the span of E1 to Vj. Right, you just move things around, right? Then it's just a linear combination of ELs, which were going from 1 to J minus 1, and EJ. Correct? So it's clear that Vj has to be in the span of U1 to Vj. Okay. And now we combine it with 6.32. What is 6.32? 6.32 was the fact that we have the corresponding statement in the previous level of the induction. Right? So we know that at j minus 1, span of V1 to Vj minus 1 is the same as span of V1 to Vj minus 1. Okay, so because we know that, and now we know that Vj is in the span of V1 to Vj, right? It follows that span of, okay, so this implies that span of V1 to Vj is going to be inside the span of V1 to Vj. So using this fact for V1 to Vj. Right? So you already know that the previous ones could not have gone outside, and then the new one fits you inside V1 to Vj. Okay, so that's the out. All right, and linearly independent is fine because we already showed that by assumption V1 to Vn are linearly independent, Vm are linearly independent. Orthonormal vectors we already proved are linearly independent, so they're both linearly independent, right? And yeah, and then the dimension part also checks out, right? Because you have distinct vectors and you have the same number, yeah? So they will span the same size of the space. Okay, so both subspace of dimension j, and therefore they are each. Is that okay? Any questions? Okay, so what have we established? Just to quickly summarize, we've established that if I give you a bunch of vectors, so if I give you V1 to Vm, you can define E1 to be this object, and Ej's you can define inductively as follows, right? By removing components from previous orthonormal vectors. And this thing will have some very nice properties. First is that it's going to be an orthonormal list of vectors in V. Okay, and secondly, if you take them successively from V1 to Vj, the span would be the same as E1 to Vj. Okay, so these are two important properties. Good. All right. So let's continue then. Okay, so now here's an example which I actually skipped. Okay, so this I'll give you as a homework assignment. The example is basically saying that, I started by pointing out that for polynomials, it's not clear how one would construct an orthonormal basis, right? So this example is basically, so it asks you to find an orthonormal basis for polynomials. Okay. So that is the example. We leave it as an exercise. So you can basically test your concepts and make sure that you've understood how to construct these orthonormal bases. Okay. Because for polynomials, like so let me quickly say. So what do we know? What is so V1, V2, right? The vectors would be what for a polynomial? What is the basis for a polynomial? One very simple basis for polynomials. It's just the monomials, right? Exactly. So x to the 0, which is like say 1 and x, right? And this is degree 2, so you'll probably also have x squared, right? But this thing is a scalar, so you don't really need to add this. So you can just have V2. Yes, it's a two-dimensional space. So these are your V2, V3. You'll have to construct E1. Let me relabel them. Let's call this 0, 1, 2. Okay, and then you have to construct E1, E2 using exactly the procedure that we discussed. Huh? We will need identity. Yeah. Okay. Yeah, that's true. Yeah, thank you. That was a dummy problem because otherwise you cannot express like a constant. Exactly. Very good. Okay. So we will. So you can use the procedure that we described previously from V0 to V2, and we can find the vectors E0. And how you do it is exactly the same. Right? So you define V0, E0 to be V0, then you define E1 to be you take E1 minus the product with E0, E0, right? Things like that, and you can construct. Okay, it's a systematic procedure. Okay, nice. Any questions about the example? You'll be able to do it, right? Yeah. The procedure is clear. Yeah. No. Is it fine? Okay. Yeah. You take a look, and if something's not clear, we can discuss next time. Yeah. No. Okay. All right, so let's continue. We finished this part. Okay, so let's move on to the next one. Yeah, so this we saw, right? So we stopped here, correct? This example is where we stopped, right? About P2. So right, so let's continue then. Here, it is asking, okay, so what is the story now? So we now answer the question about existence of orthonormal bases. So okay, so what we said so far was, if I give you a basis, given a basis, yeah, actually it's just yeah. In the previous thing we said, given an orthogonal list, you can construct a corresponding orthonormal list with like some properties about the span. Now we're going to generalize it to say that okay, so it's just a corollary of what we the Gram Schmidt procedure. It says that every finite dimensional inner product space has an orthonormal basis. How do you prove this? Given everything you've seen? Any ideas? Anyone? How would you show this? So what do we have to show? We have to show that if you have a finite dimensional inner product space, we want to show that it will have an orthonormal basis. Okay, so what do we know about finite dimensional inner product spaces? We know that every space has some basis, right? So we know that there is some list V1 to Vn such that span of V1 to Vn is the basis itself equals V, right? And V1 to Vn are linearly independent. Right? That's what it. I mean, this is true for any vector space. Right? This we can always do. So given this, right, and the statement we just proved, right? So using Gram Schmidt. So using Gram Schmidt on V1 to Vn, right? What do we get? We get a bunch of vectors, E1 to En, right? And E1 to En have what property? They have the property that they're orthonormal. Right? We just proved this, right? Using all the like removing all the overlaps and all the components. So this is going to be orthonormal. And we also said, what did we say about the span? We said span of V1 to Vn is the same as what? Span of V1 to Vn, right? So then we're done. Right? It's a basis. We have an orthonormal basis. And we also know what? We know that orthonormal list is also linearly independent, right? Okay. So is the corollary clear? That every finite dimensional inner product space is going to have an orthonormal basis. So it's quite a general statement. Okay. Okay. So formally, what is it saying? It's saying the same thing, right? So suppose V is finite dimensional. This is just summarizing what I just said. Okay. So V is a finite dimensional space. You choose some basis for V. You can always do that, and then you apply Gram Schmidt use on this basis, and you produce an orthonormal list. And this orthonormal list will have length, dimension V. It'll have dimension V elements. Okay. And this corollary was basically saying that every orthonormal list of the appropriate length is also going to be an orthonormal basis for. Okay. So this would mean that this orthonormal list is also a basis for. Right? Clear? Yeah. Okay. Very good. Okay. So let us continue. And okay. So here it is saying the following. So sometimes one needs to know not only an orthonormal basis exists. One needs to know not only that an orthonormal basis exists, but that every orthonormal list can be extended to an orthonormal basis. Okay, so we said that. So what is the statement above say? It said that for all finite dimensional spaces, one can. Okay, so there exists a an orthonormal basis, right? That's what the statement the corollary we just looked at said, right? Now it is asking something stronger. It is saying that, so if I give you a partial list, so suppose I give you E1 to EK, okay? And the space is say dimension, so dimension of V say n, K is less than n. The question is, can I extend, so given these are orthonormal, can I extend this set to form an orthonormal basis? Clear? What is happening? You understand the difference, right? Okay. So now the next corollary is going to do exactly this. So you're going to start with an orthonormal list and you're going to extend it into a basis. Yeah, we've done this already for linearly independent vectors, right? We said that if you have a few linearly independent vectors, Hoffman and Kunz, we looked at how you can extend it to produce the entire to produce enough linearly independent vectors so that it spans the set and therefore makes it basis. So we'll do something very similar here. Okay. So the statement is as follows formally. So let me write the statement. Okay. So the statement is the following. So it says, suppose V is finite dimensional, then every orthonormal list of vectors in V, okay, can be extended to an orthonormal basis for, yeah, statement is fine. Okay. We only have about a few minutes. Let's see if we can. The proof is also not too long. So let's see how the proof asks us to think about things. Let me make just a little bit more space before we do that. So, okay, so let's start. So it says, suppose that E1 to EM is an orthonormal list in V. Okay, so you have some orthonormal list which is given to you. Okay, then you already know that E1 to EM are linearly independent. This is already fine. You already proved this? Yeah. Okay. Okay. Now we know we proved this in Hoffman and Kunz. Excuse me. That this list, this meaning this one here, can be extended to form a basis. Okay, because we know that if you have a bunch of orthogonal vectors, linearly independent vectors, you can extend it to make a bunch of linearly independent vectors that span the whole space. So you can make the basis. So suppose you do that and you get E1 to EM and you have V1 to VL. Okay. Is that okay? Is it making sense? Any questions? Tell me if there's something's not clear, you can always ask. Is it making sense? Okay, okay. Great. So this is fine. Okay. And now what we're going to do is we're going to apply the Gram Schmidt procedure above. Okay, so apply the Gram Schmidt, okay, later. So now what we're going to do is apply the Gram Schmidt procedure. The Gram Schmidt procedure on E1 to EM, V1 to VN. Okay. To get a bunch of new vectors, to get E1 to EM, F1 to Fn. Okay, so you'll get some new vectors. But you notice I get these vectors to be the same. Yeah, that is, you see that I was a little bit implicit in what I'm writing, but you can check. So here's the claim that the first M vectors will remain unchanged. Okay, and intuitively it is because they don't have any overlap. Right? We removed all the overlap, so none of the terms will contribute. So we had EJ minus something, but there's something that will not contribute at all. Okay, that is the intuition. So this I leave as a small exercise for you to check. Okay. So these vectors are the same, and the guarantee of Gram Schmidt is that these guys are also orthonormal. The whole thing is orthonormal, right? And the span property is also coming from the same Gram Schmidt procedure, right? So we have also that the span of E1 to EM, F1 to Fn is going to be the same as the span of E1 to EM, V1 to VM. Correct? The spans will also match, which means E1 to EM, F1 to Fn is an orthonormal basis. Right? This is what we want. Is it okay? Is it making sense? Okay, I think that's a good time to stop. Thank you so much.